Okay then, so for energy production, we're going to start with just simply looking at the different sources of energy that we use. So one key thing to start off with is that from source to actual electricity that we get out, we never have 100% efficiency. So we're always going to have some form of energy loss. So that could be sound, that could be heat, that could be that we had impurities in our fuel, but for whatever fuel we use, we're always going to end up with some degraded energy. And this term degraded is very specific in the IB. So what it refers to is energy that is no longer available for useful work. Now, hopefully from topic 2, you're happy with the idea that energy is never destroyed, it's always just converted into different forms. So a good example of degraded energy, if I'm thinking about producing electricity from a wind turbine, then any heat loss from friction, for example, cannot become electricity. So that would count as degraded energy, because while heat may be useful in some contexts, for the context of creating electricity, it's not actually useful. So the main examples that you should be able to think about are basically heat loss for anything like cooling towers or fuel combustion, as well as friction, and then sometimes transmission losses between the plant and the house. And as well as knowing the sort of written definition, we also need to be able to know how to show it diagrammatically. So what's going on with my spelling? Already making mistakes with simple words. So the diagrammatic way is a Sankey diagram. And the Sankey diagram starts with all our energy going in. So let's say this is 100%. Now, often on this, they'll tell you that this is, say, 100 joules. And then what will happen is, as energy is wasted, they'll draw arrows off. So that would be, say, thermal losses. And that could be equal to 30 joules, which would mean that the leftover useful energy I've got going from that would be 70 joules, because like I said, energy is always conserved. And the thing about a Sankey diagram is it always goes in chronological order. So whenever you're asked about which arrow corresponds to which type of energy loss, then this is where we're starting with fuel, so right at the beginning of our process, and then this right at the end would be electricity. So you would identify which loss comes in which order. So it's also required for you, well, to be able to draw this Sankey diagram, you need to have a basic understanding of the principles of energy production. So let's say we have a general fuel power plant. So let's say this is something like a gas-powered power plant. Now, the key steps of energy production are, number 1, we always have to burn the fuel. So this would be applicable to coal, biomass, for example. We burn the fuel, and then hot air rises and drives the turbine. For any sort of combustion plant, it's never actually the fuel that's sort of moving or creating the electricity. It's always the air that's heated up by it. Then once the turbine's turning, the turbine drives a generator. So both the turbine and generator will spin at the same rate now. And with the generator, what happens is you've got a coil rotating in a magnetic field. And from topic 6, hopefully what you remember, we can draw a quick diagram to the right. If I've got any sort of wire, so if this is my wire, and let's say this is the current, and I've got my field going, let's say it's into the board. Actually, sorry, we don't want the current yet, but let's say the field's going into the board, and I've got my wire, and let's say the wire moves to the right. Well, we can use our left-hand rule from topic 6, and that would predict that, well, remember that we can treat our left-hand rule as like an FBI gun. So the force, which is the motion, is to the right. The B field is into the screen, so the current is going to point downwards. So what this shows us is that by having a wire moving in the magnetic field, we're going to induce a current. Okay, so there's I. I'll just put left-hand rule. So I think I said in the description of this event, actually, it's a really good revision for all the other topics that you do as well. So this coil rotating in the magnetic field, number 4, produces current in the coil. So current and voltage in coil. And then obviously that's stored. Now for higher level students, this would not come from your exam, but also just think about the fact that it's AC. So we've got EM induction coming up later. I think it's about in a week and a half's time, where we'll look at alternating current. But think about how a rotating coil may be relevant to producing an alternating current instead of a direct one. Okay. So we've looked at what happens when we burn the energy sources. Let's have a very quick slide on some different energy sources. So interestingly, they expect you to know that overall, pretty much all energy comes from the sun. Okay, so all of the biomass and coal and oil we use originally came from photosynthesizing plants, whether they were consumed by animals after that, but all the energy that came to producing the organic matter that broke down into oils and gases actually came from the sun's energy. Then, other than that, you should be able to identify some renewable sources and some non-renewable sources. So, just to very quickly list them off, I could ask you, but I mean, this is quite a short list, so it'll just be quicker to put them in myself. But just if you think about them as well. So we have wind, tidal, geothermal, solar. Depending on how quickly we use it, biomass could potentially be classed as a renewable fuel. And then the non-renewables are coal, oil, gas, and importantly, nuclear. So lots of people say that nuclear, they think it should be renewable because we don't actually use a huge mass in our reactor. The other thing is, new uranium isn't being produced. So by that definition, it's non-renewable. Okay. So what we'll do is we'll do one more slide and I'll see if anyone has any questions. So thinking about the different types of energy we have, you need to have some way to actually be able to compare how good is an energy source compared to others. So what we have is we have the specific energy. And hopefully, if any of you were at my webinar on thermal physics, remember what we said about the word specific in physics. Now, specific always means per unit mass. And actually, even in my dissertation that I was just writing about half an hour ago, I was referring to specific enthalpies. And even at uni level, specific just means per kilogram. So the specific energy of a fuel is the amount of energy delivered by 1 kilogram of a fuel. And then you could potentially say when combusted, because normally, sorry, when combusted completely. As normally refers to combustion, but as we also have energy densities and specific energies of uranium and renewable energies, which obviously don't come in, you can't get a kilogram of solar, but that we can still apply the same energy, specific energy idea. And then the other one we have is the energy density. Well, if we relate this to the mass density is the mass per unit volume. So the energy density is just the amount of energy delivered by 1 meter cubed of a fuel. So actually in terms of, and again, we could use the same little bit of words afterwards. Now we could use either, but if you think about the difference between specific energy and energy density, well, if we know the volume of fuel that we're going to be combusting, that's actually more useful in terms of working out the size of a reactor we need, how much storage we'd need to be able to have enough to provide for the daily requirements. So actually, the energy density in a lot of ways is much more useful to us than a specific energy. Now let's look at the units, because I always say that in an exam, if you're stuck on how to answer a question, the units can often help. So the definition here is energy per kilogram. So the units, which I'll always put in square brackets, are joules, or maybe kilojoules, or maybe even megajoules per kilogram. And this is delivered by 1 meter cubed. So it's the energy again, so joules per meter cubed. Now let's look at these two values. We can go from one to another by, well, let's look at the specific energy. If I times it by kilograms, I get rid of this. And if I divide by the volume, I get into energy density. So we can say that the energy density, which I'll abbreviate as ED, is equal to the specific energy times by, and then it's something with the units kilograms per meter cubed, which hopefully, if we look at our definition of energy density, this is just the mass density, because it's the mass per meter cubed. So it's equal to the specific energy times the density. Okay. And similarly, we can find the specific energy by doing the energy density divided by the density.